Great paper from Google, CodecLM. Aligning language models with tailored synthetic data. Large language models (LLMs) are increasingly impressive in their ability to follow instructions and perform diverse tasks. Instruction tuning, where LLMs are fine-tuned on human annotated data or knowledge from stronger LLMs, is key to aligning these models with specific tasks and user goals. However, the cost and scalability of human annotation present challenges. This is where CodecLM steps in, offering a novel framework for automatically generating high-quality synthetic data tailored to specific tasks and LLMs, eliminating the need for human annotation. LLM as a codec, encoding and decoding instructions. CodecLM cleverly utilizes a strong LLM as both an encoder and decoder in its data generation process. Encoding, seed instructions, which represent the target task or domain, are first encoded into instruction metadata. This metadata acts as a concise summary of the instruction distribution, capturing two key aspects. Use case. This describes the intended task, like question answering, creative writing, or code generation. Skills. These are the specific knowledge areas the LLM needs to effectively respond to the instruction, such as Python programming or academic writing. For instance, the seed instruction, as a sports commentator, describe the winning play in the final seconds of a championship game, would be encoded with the use case, creative writing, and the skills, role play, sports. Decoding. The encoded metadata is then decoded to generate tailored instructions. This starts with a strong LLM generating basic instructions based on the metadata constraints. To enhance these instructions and better align them with the target task, CodecLM employs two key techniques. Self-rubrics, tailoring instruction complexity. Self-rubrics dynamically adjusts the complexity of instructions based on the metadata. Here's how it works. Rubric generation. The strong LLM creates metadata-specific rubrics for assessing the difficulty of an instruction. For example, for the use case, business plan development, and the skills, market research and planning, the rubric might emphasize the need for competitor analysis and financial projections. Action generation. Based on these rubrics, the LLM generates corresponding actions to increase the complexity of the basic instructions. These actions are specific and relevant to the domain, unlike generic human-crafted rules. In our example, actions could include add SWOT analysis or compare with market competitors. This process allows for generating instructions that are challenging and specific to the target task, leading to more effective LLM alignment. Contrastive filtering, selecting impactful instructions. Not all instructions, even complex ones, are equally effective for LLM alignment. CodecLM addresses this through contrastive filtering, which selects the most impactful instructions for fine-tuning the target LLM. Quality gap measurement. The process involves comparing responses from both the strong LLM and the target LLM for a given instruction using a scoring function. This function assesses the quality gap between the two responses, indicating how much the target LLM can potentially learn from the strong LLM. Instruction selection. Instructions where the target LLM performs significantly worse than the strong LLM are prioritized for fine-tuning. These instructions expose the target LLM's weaknesses and encourage improvement in those areas. Additionally, instructions where the target LLM excels are fed back into the self-rubrics process for further refinement, leading to increased data efficiency. Contrastive filtering acts as a quality control mechanism, ensuring that the LLM is trained on the most beneficial and informative instructions. CodecLM's effectiveness. A look at the results. Evaluations on various open domain instruction following benchmarks demonstrate CodecLM's effectiveness in aligning LLMs with diverse tasks. Compared to existing data generation methods, CodecLM consistently achieves superior performance with different LLM architectures and dataset sizes. This highlights its ability to adapt to different scenarios and efficiently utilize data for LLM alignment. Looking ahead, future directions and considerations. CodecLM offers a promising approach to LLM alignment with its ability to generate tailored synthetic data. Future research can explore richer metadata, expanding the scope of metadata to include finer-grained aspects of instructions can further enhance data tailoring. Improved prompt design. Utilizing advanced prompt optimization techniques can lead to even better instruction generation and LLM interaction. Reliable scoring systems. Integrating more robust and comprehensive scoring functions can improve the selection of impactful instructions. While CodecLM presents exciting possibilities, ethical considerations are crucial. Since the generated data inherits biases and limitations from the strong LLM, it is important to employ techniques for mitigating bias and ensuring fairness. Additionally, addressing vulnerabilities like prompt injection attacks is necessary for robust LLM applications. In conclusion, CodecLM provides a valuable tool for adapting LLMs to specific tasks and preferences. With continued research and development, this framework has the potential to revolutionize the way we train and interact with large language models.